All right, hello everybody. Welcome. Today's Thursday and Friday this week. I'm gonna have two videos for you guys. I'm gonna just bum rush you with information about experiments and observational studies. These two things right here. There is a lot of information that we're gonna cover in these 2 days, and it's kind of dense vocabulary as well. There's lots of things, but uh, we kind of need to know all of this stuff before we can start conducting experiments. So the plan here is this, right? Thursday, Friday this week, you're going to get bum rushed with information about experiments and observational studies, mostly experiments. And then we're probably going to take like the next 2 weeks, in fact, maybe 2.5 weeks, basically through our conferences, where we're going to apply this stuff, right? We're going to do experiments. We're gonna look at people who are good at experiments and that kind of thing. So it's gonna feel like a rush of information today and tomorrow, but hopefully over the course of the next 2 weeks, we're gonna get more comfortable with it as we move on. Okay, so it's gonna be uncomfortable in the beginning, but as we do more, you should feel more comfort over it. And then this is actually the last chapter of our unit, right? This unit is almost finished. There's only 3 chapters on it. But like I said, we are going to spend a significant amount of time making sure we're comfortable with a lot of this vocabulary over the course of the next 2 weeks. All right, so let's just jump right in here. So an observational study. An observational study is where researchers don't assign choices, they just observe them. So a study in general here, we're not talking about sampling anymore. We're talking about researchers who are trying to figure something out about a situation, okay? So there's different types of observational studies, and this one is where the researchers are not assigning a choice, right? That's important. They're not assigning choices. They're just observing them, okay? They're just observing what people are doing in their environment here, okay? The text example looked at the relationship between music education and grades. They simply went and found, they compared the grades, they took a group of students and they compared the students who had music education and looked at their grades, and they compared them to the students who did not have music education and looked at their grades. They didn't have to talk to these students at all. They could gather all of that information off of a computer somewhere, okay? They didn't assign a choice. They simply observed what was happening, okay? Since they're not assigning students to get a music education and just observe the students in the wild, right? Meaning not like students like in the jungle attacking each other. In the wild, meaning like just the students that are taking education or music education courses. We call it an observational study. We were observing what people do, and then we were recording our results. Okay, that's an observational study. There's 2 types of observational studies. The first here, it's called a retrospective study. The researchers in the text example first identified subjects who studied music and then collected data on their past grades. This was a retrospective because we were looking at it in the past, right? We were looking at it retro, something in the past. We identified people who studied music, and then we went back and looked at their grades. So it's a retrospective study. We also have these things called prospective studies. And a prospective study is when the researchers identify subjects in advance and then collect data as events unfold. So this would be like in the music education study, it'd be like talking to a group of middle school students, and then finding some students who had music education in middle school and then not, and then following them for 5 years and looking at their grades every year as they go, right? They're looking at them in advance and then they're following them. That is a prospective study. And prospective studies usually take a significant amount of time before they're finished. In fact, many studies will record things like there's been studies done on twins. Like it's actually a really interesting field, studying people who are twins or triplets. They'll record things about them when they're babies, and then they will follow them for 20 years or 30 years. and they'll record, like every couple of years, they'll come back and talk to the twins or have the twins take a survey, and then they'll see where they went in 30 years. Again, prospective study, because we're talking about identifying them early and then following them, rather than a retrospective study which identifies them and looks at their past. Okay. Observational studies. Observational studies are valuable for gathering trends and possible relationships. They don't tell us about a cause to effect. They tell us what we can find, not necessarily when one thing causes another thing, right? We call this thing a causal relationship. These observational studies do not, I repeat, it is not possible for them to show a causal relationship. And that is a big misunderstanding that happens a lot. But these do not they do not show a causal relationship, meaning we can do everything with that music education and grades. We can show that there's a trend, but we cannot prove that taking a music education class will improve your grades in the future. We can say that there's a trend. We can say that there is a possible relationship between them because students who are in band or in orchestra have higher grades than those who are not in that. We can show a possible relationship, but we cannot prove. There's no proof that there is a causal relationship that music education increases grades. It's just a possible relationship. It's governing a trend. Sometimes observational studies are used as sort of like a jumping off point for other research. So you can't prove a causal relationship. They're just good for discovering trends and possible relationships. Now let's talk about a randomized comparative experiment. A randomized comparative experiment, when done well, is a study that allows us to prove a cause and effect relationship. So observational studies can't, but experiments, when done well, can prove a cause and effect relationship. However, performing a good experiment is often a very difficult thing to do. In fact, we're going to spend 2 weeks talking about experiments, and that's just going to scratch the surface on how you really do a good experiment. Okay, you can take an entire master's level course in college about how to do a good experiment. So we're scratching the surface here. Okay, in an experiment, right, the experimenter must identify at least one explanatory variable, called a factor, to manipulate, and at least one response variable to measure. Okay, so the explanatory variable is the thing that we're manipulating to try and see if it has an effect on the response variable, right? So we might call the explanatory variable the cause. Okay, that you can't read. That's a terrible writing. But you might call the explanatory variable the cause, right? And you might call the response variable the effect. This variable is causing a change in this variable. The explanatory variable is causing a change in the response variable. So we're manipulating the explanatory variable to see if it's having a change on the response variable. Okay. An experiment manipulates factors or factor levels to create these things called treatments. Okay. It randomly assigns subjects to these treatment levels, and it compares the responses of the subject groups across treatment levels. So we're manipulating the factors, and we'll talk about what it means to be a factor level, but we're manipulating factors. We are randomly assigning subjects to these treatments, and then we are comparing the differences in the group. And because we're making the people do something, right? We're assigning a treatment to them. That comparison at the end does allow us to determine a cause and effect relationship. Experiments done well can show a cause and effect relationship. Observational studies cannot. So more about randomized comparative experiments. In an experiment, the experimenter actively and deliberately manipulates the factors to control the details of the possible treatments, okay, and assigns the subjects to those treatments at random. So again, we're still using randomness as a tool in order to find out these differences. The experimenter then observes the response variable and compares responses for different groups of subjects who have been treated differently. So we're going to give two different groups a different treatment, right? They're going to get treatment 1, and this group is going to get treatment 2, and then this group up here, they all received treatment 1, and this group of people over here, they all received treatment 2, and then we're going to compare those responses, and we're going to see who did better, treatment 1 or treatment 2. And that allows us to prove that cause and effect relationship. We're going to randomly assign people, right? We're going to randomly assign people into the two treatments. That's going to help us get rid of bias. And then we're going to give them the treatment, whatever it may be. And then we're going to compare the results at the end. And doing that process allows us to create a cause and effect relationship. In general, individuals on whom or which we experiment are called experimental units. These could be people. These could be plants. These could be candy bars. They could be anything, right? It's an experimental unit. It's whatever we're performing the experiment on. In one case, if you guys look in the back of the room, you can look right now. The one on the far right that says name brand storm brand. That was an experiment that was done a couple years ago where the experimental unit was a tampon, okay? So it can be anything. When humans are involved, we typically call them subjects or participants, right? Because we're nice to humans, we don't call them experimental units, we call them subjects or participants. Like, thank you for being here, you are a participant. You are not an experimental unit, right? We're not that, far removed from the experimental process. The specific values that the experimenter chooses for a factor are called the levels of the factor. Meaning that, let's say I wanted to give somebody, we wanted to test the effectiveness of a drug, right? We might have one factor, one level that is full dose. They get a full dose of the drug. And we might get another person who gets a half dose. And we might get another person that gets a sugar pill, which would be no dose, not like the drug no dose, just not a dose of it. So that would be 3 levels of a particular factor, right? The factor is, does this drug have an effect? One level would be a full dose of that drug, one level would be a half dose of that drug, one would be no dose of that drug, but you still have to give them something, so you give them a sugar pill, but you don't tell them that it's a sugar pill, okay? That's called a placebo, and we'll talk about that tomorrow. A treatment is a combination of specific levels from all the factors that an experimental unit receives. So this up here is treatment 1, this right here is treatment 2, and this right here is treatment 3, okay? This is the full dose treatment, this is the half dose treatment, and this is the placebo treatment, the sugar pill treatment, okay? You can have multiple factors in an experiment, which means that a treatment can be a combination of factors. And we will look into that tomorrow, right? This is a simple experiment with one factor, which creates 3 different treatments, right? One factor with 3 levels, which creates 3 different treatments. We'll look at more complicated ones tomorrow. There are 4 principles of experimental design that we want to make sure that we are trying to attain in every single experiment that we do. Those 4 treatments, these 4 principles are the big 4 pillars that we need to be thinking about every time we perform an experiment. So let's look at those in a bit of detail here. The first is control, okay? We need to control sources of variation other than the factors we are testing by making conditions as similar as possible for all treatment groups. Okay? Let's go back and just really quickly think about that drug treatment one that we did, right? And let's just simplify it to say full dose, no dose. Okay? We want to see whether or not this drug is having an effect. Well, we have to be careful because while these two things might be having an effect, there might be other variables in a person's life which might be having an effect on this, right? Maybe we're looking to see if a particular drug has an effect on obesity. Well, if we took a group of people and we randomly assigned them to a full dose or no dose of this treatment, we have to be very careful and say, you guys need to stick to this specific diet. Because what if we had a bunch of people in the full dose group who were on a diet and were exercising regularly, were eating less calories, but the people in the no dose group were like, I don't care, give me that ham, right? And they're just going to eat an entire ham or turkey or right? They're not on a diet and they're not trying to lose weight. They're not exercising. You could find that the full dose people lose weight and become healthier, and the no dose people don't, and that could have no effect on the drug, right? That might just be because the full dose people are living a healthier lifestyle, and so they're losing weight. So we have to control outside sources of variation, because if we don't, we might think that this drug is having a big effect when in reality, in our group, we just had healthier people in our group, okay? Part of that is going to be solved by randomly assigning people. But the other part of that is whenever we're doing an experiment, we have to control these outside sources of variation. Other factors that might affect the results, we have to control them and make sure they're the same for every treatment. So the second one is randomization. Randomization is going to help us control, okay? The big thing that it does is it allows us to equalize the effects of unknown or uncontrollable sources of variation. So even if we do our absolute best to control outside effects, there will still always be unknown or uncontrollable sources of variation, things that are going to change that cause variance in the results. By randomizing people into the two groups, we can help control those effects, right? If I randomly assign people to full dose and no dose in our obesity pill, right? Those people with healthier lifestyles are likely to be split up into the two groups, whereas the people without healthy lifestyles will also be randomly split into the two groups, making sure that those two groups are what's the word I'm looking for? So that the variation that's being caused by those two types of people is not affecting our overall results. So randomization is an element of control, right? Is an element of control. In fact, it's an essential element of control. Right? I should put that essential word in there, right? Right in there. It is an essential element of control because it allows us to control unknown or uncontrollable sources of variation. We can do our best planning to control things, but there will always be factors outside of our control or that we just flat out don't know about. Randomization takes care of those things. It does not eliminate the effects of these sources, but it spreads them out. So it spreads them out across the treatment levels so that we can see past them. So they're not going to overly influence one thing over another. Without randomization, you don't have a valid experiment, and you will not be able to use these methods of statistics to draw conclusions from our study. Basically, if you don't have randomization in your experiment, what you have done is useless. Okay, you have no basis to say anything about your subject if you don't randomly assign people to treatments. Can't do it. Okay, next thing is called replicate or replication. We need to be able to repeat the experiment, applying the treatments to a number of subjects. So if I have that full dose, no dose thing, it's not okay for me to send one person up to the full dose, right? If I have one participant in the full dose and sorry, I'm trying to draw a box. And excuse me. And we have just one participant. Even if they have been randomly assigned, there's one person to here and one person to there, putting one in each group does not really prove anything, okay? We need to be able to apply the treatment to a number of subjects. So we have to be able to replicate the results. Outcomes of an experiment on a single subject is called an anecdote, not data. And anecdotes are not proof of anything, right? They call it anecdotal evidence, and it doesn't fly in court and it doesn't fly in statistics. When the experimental group is not a representative sample of the population of interest, we might want to replicate an entire experiment for different groups in different situations. So sometimes, instead of just making sure we have multiple people in each one, we might want to redo this experiment like lots and lots of times. This is me making the diagram for this experiment several times. You might want to, if we can't get a representative sample, in fact, most times when we do like drug trials and stuff, we need to do multiple experiments in order to show that some change is being made. Okay. So replication, that's number 3. And the final one is called blocking or blocking. And the blocking one is actually not it's not a essential, but it's really strongly recommended. Okay. So sometimes attributes of the experimental units, read that as attributes of people that we are not studying and that we can't. Let me try this again. Sometimes attributes of the experimental units that we are not studying and that we can't control may nevertheless affect the outcomes of an experiment. If we group similar individuals together and then randomize within each of these blocks, we can remove much of the variability due to the difference among the blocks. So let me give you a quick example of where we most commonly see that. Do I have another thing there? Let's do it. So no, blocking is an important compromise between randomization and control, but unlike the first 3 principles, it is not required in an experimental design. It's just strongly recommended. Okay. So let me give you an example. I'll use this space up here. In drug trials, we often block by gender. Okay. So we will often first block a drug trial by gender. And the reason why we do that is because boys and girls are different. Okay. If you don't know already, boys have penises and girls have vaginas. Okay. This isn't the health class. Hopefully you know that already. Males and females have very different anatomies. And the reality is that when we're studying a drug trial, they may a certain drug or a certain chemical may affect males different from females. So if we go back to this obesity pill that I made up, we might consider blocking by male first, and then splitting up our 2 treatments, full dose, no dose, and doing 2 separate trials. Okay. And the reason why we do this is because our anatomies are different. And since we know that anatomies between males and females are different, we try to control that in the beginning by saying, okay, I know males and females are different, so I'm going to split them into 2 groups, and then I'm going to do a male full treatment and a male no-dose treatment, and then I'm going to do a female full treatment and a female no-dose treatment. That way, the inevitable differences between men and women is not having an effect on our treatments. We can compare the male treatments and we can compare the female treatments, and we know that the variability caused by gender is not having an influence on what we're doing over here with the treatments on the drug, right? So blocking is sometimes used to reduce variability due to effects that we know about. We also tend to block things by race sometimes because there are slight differences between the anatomies of different races. And we also will block, I mean, there's a lot of reasons why we'll block. Okay. Gender is one of the most common ones. So that is the 4th and final principle of experimental design. Now, the last thing here, which I've kind of been doing all along, actually 2 more things before we look at an example. This I've been kind of doing all along, right? We diagram experiments. This is just a good way to visually show the separation of treatments, right? So we can follow a diagram to know kind of what we're doing. So we randomly apply people to 2 groups, and in those 2 groups we apply them to a different treatment, and then we can compare the different treatments. I've kind of been doing that diagram all along, so it's not, I'm not going to spend a lot of time on this thing right now, right? The last thing before we look at an example is that last comparative step. How large do the differences need to be to say that there is a difference in the treatments? Um, if things are like one measurement apart, are they okay? Two measurements apart, okay. How do we know? Okay. So what we'll say for now is that differences that are larger than we get just from the randomization alone are called statistically significant results. Meaning that if we believe that the results that we have seen could not be caused by randomness, then we would call those things statistically significant. If the difference between the two treatments is so large that randomness could not be the thing causing it, then we'll call that statistically significant. Again, using our full dose, no dose treatment, right? If I'm comparing the results, the overall weights at the end of the full dose, no dose, if the people who took a full dose of the drug for this long had lost like a lot more weight than the people of no dose, we would call that statistically significant. And when I say a lot more, I mean so much more that it couldn't have just been the random people in the group causing it. It had to have been the treatment making that effect. Now, we do actually have a number that we can calculate to look at that, but that's what we do from January to March. That's called inference, right? We're seeing if the difference is so big that randomness couldn't have been a factor. So yeah, that's what we're going to do later in this course. That's like the last month that we're looking at it, okay? Let's do this example, and then that'll be the end for today. So we're going to keep it right around 30, a little over 30 minutes, right? Yeah, that's pretty good. So, an ad for Optigrow plant fertilizer claims that with this product, you will grow juicier, tastier tomatoes. You'd like to test this claim, because obviously Optigrow is going to say that, so we want to test that claim. And you wonder whether you might be able to get by with half the specified dose. That should say dose, right? Ignore that. It says dose. Half the specified dose of Optigrow. How can you set up an experiment to check out that claim? So let's go through a number of steps that we need to think about when we are conducting an experiment. So the first, we're in the planning stages, right? We want to plan something. So we want to state what you want to know. So in this particular instance, I want to know whether tomato plants grown with Optigrow yield juicier, tastier tomatoes than plants raised in otherwise similar circumstances, but without the fertilizer. I want to compare tomatoes that were grown with Optigrow and tomatoes that were not grown with Optigrow and see if the Optigrow ones get bigger and juicier, and tastier than the other ones. So that's what I want to do, okay? What's my response? What am I looking to measure in the end, okay? Right? Specify the response variable. Same like with the simulation. What am I measuring in the end? Well, I want to evaluate the juiciness and taste of the tomatoes. And so to do that, I'll ask a panel of judges to rate them on a scale from 1 to 7 in juiciness and in taste. Okay? This is kind of subjective. Sometimes when we look at a panel of judges, we might want to say that we get like experts in the field to really look at it. So we're going to get expert tomatoists, right? So judges, they're going to be expert tomatoists. I don't know if that's actually a job or not. Maybe we could just call it a cook. Maybe we'll just get really good chefs to come out and eat the tomatoes. But anyway, I'm going to call them expert tomatoists because I think that's cooler sounding. So we're going to rate them on a scale from 1 to 7 in juiciness and taste. That's our response variable. Okay, what are our treatments, right? We want to specify the factor levels and the treatments that we're going to be using. The factor, the thing that's changing that we're manipulating is the fertilizer, okay? Specifically Optigrow fertilizer. So I'm going to grow tomatoes at 3 different factor levels. Some with no fertilizer, some with half the specified amount of fertilizer, and some with the full dose of fertilizer. Those are my 3 treatments. A treatment that is none, a treatment that is half, and a treatment that is full. What are my units here? What am I looking at? Well, I'm going to take 24 tomato plants. of the same variety from a local garden store. Notice that I'm taking the same variety, right? That is important as a measure of control. If I got two different varieties of tomatoes, one of them might be tastier and juicier just because it's a better variety of tomato. So I'm controlling that variable by taking the same variety. Also, I'm controlling something from the local garden store, because if I buy my tomato plants at Thompson's Garden and I buy my tomato plants at Home Depot, the likelihood is I'm going to get better tomato plants from Thompson's. And if I had a mix of Home Depot and Thompson's in there, maybe I'm going to have tastier, juicier tomatoes because Thompson's makes better tomatoes than Home Depot does, right? So I'm controlling that element by buying everything from the same local garden store, right? Thompson's Garden. Let's talk about some of these other control elements that we're going to do. Remember, control means we're going to set the standard. We're going to make everything the same. Okay, so I'm going to locate farm plots near each other so that they get similar amounts of sun, rain, and experience similar temperatures. So I'm going to put a plot on the side of my house, and they're all going to be right next to each other, because if they're all right next to each other, they're going to get the same rain, the same sun, the same temperatures. They'll also get the same other types of, the same kind of soil conditions as everybody else. Because again, these are all different variables that might influence how tasty and juicy my tomatoes are. So I want to make sure that everybody in the group gets those same experiences, so that the only factor that is changing is the fertilizer. I'm also going to weed the plots equally and otherwise treat the plants alike, right? If I play classical music for one of the plants, I'm going to play classical music for all of the plants, right? If I'm going to play rock music for one of the plants, I'm going to play rock music for all of the plants, because these are elements that can affect the tomato plants that are not the fertilizer. And I want all of these ones to be the same for every tomato plant, okay? For the replication, I'm going to use 8 plants in each group. I bought 24. I have 3 groups. I have 3 treatments, so I'm going to put 8 in each. I'm going to randomly assign them to treatments. So I have 24 plants. So I'm going to label the plants with numbers 00 to 23. I'll look at pairs of digits across the random number table. The first 8 plants identified, ignoring all these ones higher and any repeats. I'm going to put in group 1. The next 8 I'm going to put in group 2. And the next ones I'm going to put in group 3. They have all been randomly assigned. This random assignment helps us control these unknown effects that the tomatoes might have. Maybe 2 of the tomato plants I bought from Thompson's have a little bit of rot on them, okay? If I randomly assign them into different groups, those effects are going to be minimized. Those things that I don't know, the things that I can't control, will be minimized. Let's make our design for this. So I'm going to take my diagram here. I'm going to take 24 plants, and then I'm going to randomly assign them to 3 different treatments. We had one treatment that was full dose. We had one treatment that was half dose. That's a nice H. Half dose. And I had one treatment that was no dose. No fertilizer. So full Optigrow, half Optigrow, no Optigrow, and then at the end, I'm going to compare them. So there's a nice diagram of this particular experiment. Once my data is collected, I'm going to compare the results of the 3 treatment groups. So I'm going to display the results in a side-by-side box plot. That's using the things that we did in the last chapter. I'm going to compare the means of the groups and see what that does. Also, finally, to ask the final question, whether or not the differences we observe in the means of the 3 groups are meaningful. That's what we're talking about with statistical significance. And I'll be honest with you, this thing right here, the greater than I would expect by knowing the usual variation among tomatoes, that's all about statistical significance. And this process is a, sig, it starts with an I, significance. This process is what we do in the last couple months of class. Okay, and I think that's it. You have an example on your paper, on your notes that says, "Oh, my ulcer, ugh, my ulcer." If you want to read that example and do that, and then you can start on your assignment after that. Thank you. I will see you guys Monday.